In this video, we introduce VILP, imitation learning with latent video planning. The pipeline of VILP consists of 3 steps. The first step is training autoencoders to compress images to latent space. The second step is training video diffusion models in latent space. And the third step is training a low-level policy which can map the generated videos to robot actions. Given the current observation, VILP can generate videos that depict robots performing specific tasks, which can be called video planning. Subsequently, these generated videos can be mapped to robot actions by the low-level policy. VILP is time efficient. We found that in VILP, a few denoising steps can generate good enough robot videos. This makes deploying VILP as real-time policies feasible. In video planning experiments, we want to compare VILP with UniPy on the ability of video generation. We implemented VILP and UniPy across 3 video datasets. There is no action generation in video planning experiments. In video planning experiments, all test cases are not seen in the training dataset. Here, 4 and 64 represents the amount of denoising steps. We can see that VILP outperforms UniPy across time consistency and quality of the generated videos. Another interesting observation is that the generated videos by VILP always have some noises. When we generate long videos, the last frames of current inference output will be the input of next inference. Therefore, this indicates that noises won't affect the use of the generated videos. More results in our paper also demonstrate the same conclusion. Moreover, VILP can generate highly time-aligned videos from multiple views, or RGBD. But UniPy lacks this ability. One interesting observation is that for VILP, the generated videos do not always maintain the exact same information, such as the object pose, as the input conditions. On the other hand, UniPy does the opposite. However, videos generated by VILP are much better than those by UniPy. We believe this is an advantage of VILP because in an imitation learning dataset, you cannot expect it to include all possible cases, like all object poses. The ability of VILP to reason about unknown situations based on the information learned from the dataset is the key to its superiority over UniPy. Next, we show experiments of imitation learning with video planning, which involves both video generation and action generation. We tested on 2 simulation tasks, nut assembly and arrange blocks. The objective of nut assembly is to insert a nut onto a pole, while the objective of arrange blocks is to push 3 blocks into a line. These tasks require fine control and high-level planning. From the perspective of video generation, as previously demonstrated, VILP outperforms UniPy. It is noteworthy that, so far, the videos have been long sequences generated by open-loop inferences. However, in imitation learning with video planning, we adopt a receding horizon planning approach rather than an open-loop method. For low-level policy training, we designed 2 action-labeled data configurations for each task, denoted as small and hybrid. Details of how these datasets be constructed is shown in the paper. The purpose of designing these datasets is to explore the extent to which imitation learning with video planning depends on action data. We demonstrate that an efficient video-to-action model can be achieved using small action dataset combined with demonstrations that differ from the target task, which indicates that VILP can rely less on extensive high-quality task-specific robot action data. In contrast, other imitation learning methods, like diffusion policy, rely heavily on action-labeled data. Moreover, echoing insights from video planning comparisons, VILP exhibits several advantages over UniPy, including faster inference times and superior video generation quality. Consequently, VILP outperforms UniPy in practical policy applications. Additionally, our findings indicate that for VILP, utilizing DDIM for 4 to 8 step denoising achieves peak performance, suggesting that additional denoising is unnecessary. Under such conditions, real-time inference becomes viable. Next, we demonstrate results on a real-world task, rearrange blocks. The task goal is to arrange two blocks, an L block and AT block, on a blue line in an LT configuration. As shown here, VILP enables real-time closed-loop fine control. Here, we present additional VILP rollout results. These results demonstrate that VILP effectively handles this challenging task, which demands high-level planning, multimodal action capture, and precise control. Successful arrangement of both two blocks is marked with a check, indicating task completion, while arranging only one or no blocks is marked with an X, indicating incomplete task performance. Finally, we present a comparison with UniPy. The videos show that when using only 4 inference steps, the actions generated by UniPy are quite jerky and fail to effectively move the block. With 16 inference steps, UniPy's inference speed is significantly slower. Excessive pauses between each action generation result in a highly disjointed action sequence, which negatively impacts performance on tasks requiring fine control and dynamic force interaction.